Итак, мы начинаем наш третий диалог. Again, we'll have Boris as Socrates asking, and me as Plato interpreting what actually happened in human culture, civilization, science over the last just 3,000 years. Boris?
Yes, and we premeditated our topic. It's not an exprompt, it's a premeditated topic. We agreed to talk about Bohr's model of atom. But let's go back in time. For how many years? Probably a few thousand years, when Aristotle came up with idea of atomic structure of the material. What do you think? What was the reason to move him toward that direction? Because we spoke in our previous dialogues, it was impossible, there was no instruments, there was no any experience or experimental way to even get close to this idea. But anyway, the power of mind, the power of intelligence, the power of human brain created a miracle, coming up with idea which has been proved thousands of years later, only because humanity had the technology. So, what's stronger, brain or technology?
Aristotle. The problem with the matter was that it, even in Greek time, it was very complicated, because even Greek knew how many different combinations of materials and matter could exist, and what happens if you change just small fraction of mixes in solid or liquid state. And of course, matter was divisible. So Greek just simply thought, what happens if we continue dividing pieces of matter or drops of matter into smaller and smaller parts? They couldn't see any of that, but they could imagine that something should go to extremely small size, but then it has to stop there. So Greek thought that an atom is something elementary, non-divisible, small, which could be brick of building out larger materials. At the same time, if there are different atoms, combined together they could create different types of matter in terms of properties, colors, and other things that did make sense to them. But that idea was, well, we can credit alchemists with attempts to create gold out of lead, copper, zinc. So alchemists probably had some ideas about structure of matter. Interestingly enough, they had more understanding of that than even actual chemists, probably because they were more driven, better motivated to create gold out of nothing.
But did they realize if their dream will come true, that the value of gold will destroy the dream itself? Because if gold would be possible to create artificially in a chemical lab, then value of gold will diminish.
Well,
but they didn't think that far.
That's why alchemy was such a competitive business. most important thing, of course, was to really create gold out of lead, zinc, copper. But second most important thing was to preserve exclusivity of that discovery. That's why so many people suffered and died out of erroneous perception that gold was created. In reality, of course, it became a lot more complex. So now we have to build gigantic elementary particles accelerators to create gold out of something else.
And the cost of that created gold will be probably much higher than the cost of
it
gold.
could be
which-
very expensive to create artificial gold.
Yes.
Nobody does it.
Yeah.
Now back to the history. So in terms of understanding of the atom, history was slow. Probably till late 19th century. Of course, history of science knows great chemists, really, even in 16th, 17th century. But that was more phenomenological, chemical science than any deep intrusion into the nature of matter, simply because energy required to really go inside the matter and approach atom is such it was out of reach of human science till late 19th century. So it took great scientists like Maxwell and great inventors like Edison and others to develop science of electromagnetic field and start extracting particles and observing atomic and quantum phenomena very late in 19th century. But of course, that all was experimental understanding, intellectual understanding of those scientific facts and experiments had to come from gigantic, monumental achievements of mathematics dated back to 1718, 19th century, with names like Newton, Leibniz, Euler, Gauss. And of course, Maxwell himself was, in a way, theoretical physicist, creator of the theory of electromagnetic field, which at the time was as much important and possibly more than Einstein's theory of relativity and quantum, deep structure of matter.
Question regarding this: the importance of electromagnetic theory, fields theory, versus Einstein. Absolutely esoteric, still esoteric, still understood by few. I believe because the electromagnetic fields and theory of that fields interaction with real world was more applicable to everyday life, and technology arrived from that. What Einstein did emerged later on to absolutely terrible things, we all know that, but at that time electromagnetic fields was actually bread and butter for technology development. Am I right? Or yeah, that's the reason. That's the reason.
Yeah, you're right.
So probably money went to that research and develop, and I would say a transition from the pure theory to applied science to technology. Something like that.
Well, course, Maxwell's theory of electromagnetic field is clear and clean, classical, top-level theoretical achievement. It has crystal clear equations, it has wonderful clear solutions, and it seemed to be perfect classical physics, classical theoretical physics until people come to realize that, and Maxwell himself of course knew it, that carrier of electromagnetic field is something. Initially they thought it's a ephemeric substance distributed in the universe, because electromagnetic field and light, which is electromagnetic by nature, just very high frequency electromagnetic field, are waves. And in order to create waves, you needed some substance, like when we look at waves in the water on the ocean. Waves in the ocean require water. Electromagnetic waves in space required something that would be flickering and propagating electromagnetic field in that matter. Initially they thought it's a theorem.
By the way, it's also a very ancient concept, came from
well, yeah, but
pre-science times, I would say, right?
Well, yeah, of course. As soon as people started analyzing waves, and initially that was obviously water, I don't think, and I don't know, whether Greeks understood that light is a wave or requires a sphere. It might came later. It was clear coming out of Maxwell equations. But it created terrible paradoxes. In the end, that perfect creation of theory, mathematical and physical, created something that opened gates to the new phase. So, light, it is a wave. But then, 15 years old Einstein asked himself, what happens when observer, person, moves with the speed of light? If light is a wave, imagine you have a boat which moves in the ocean with the speed of wave. So it goes with the wave. Wave cannot escape it. Observer moving with the speed of light will never see anything, because light cannot separate from him, cannot escape. He moves with light. Result is that he loses sight. He doesn't see anything in front of him. Yeah, because nothing, a light is with him or behind him if he moved faster than light. And that is impossible according to a Galileo principle. So as long as observer moves straightforwardly with a constant speed, nothing, no experiment could establish that it is moving. And Einstein understood that when you lose sight, you clearly understand that something happening, something changed. And that's how, from his young age, on the basis of Maxwell theory, he was challenged with that paradox that he resolved. When he really became 25 years old man.
Yeah, I'm sorry for interrupting. You said that Einstein was 15 years old. there is almost like a joke that he was a bad student in high school.
He was.
And his teacher told him that he can be anyone, but not a mathematician or scientist or whatever, a janitor, butcher, baker, shoemaker, whatever, but not a scientist. I'm not going to abuse people of that profession. That's a very important things for everybody. But what do you think? What happened in his brain? Why did he ask that question? Because as a matter of fact, from my understanding, in science, sometimes the question is more important than anything else. Because the right question leads to the discovery. Until there is a question, there is no discovery.
Boris, it's a great paradox. Yes, he was not a very good student initially. But he was always, all his life, he was deep thinking philosopher, even when 15 years old. And that's what, if you think of it, that imaginative experiment with the observer moving on the front of light with the speed of light, it is not mathematical. It's imaginable experiment, a very genial thought which could come to mind of any child, not even very good mathematician, but that was him. Normal child, sometimes very good mathematician, would never think about it. She doesn't have time for that, such a stupid things. And if he or she ever thought about it, he would not spend his valuable time exploring that paradox. But Einstein did, probably because he had nothing better to do for 10 years. So he did, and he, of course, besides him, there were Lorentz, Poincaré, others, who really took Maxwell equations and pushed them to the limit and solved that paradox. What Einstein did was pure, or almost pure philosophy around Poincaré and Lorentz mathematics. And he was a philosopher. He really became great when he moved further, another 10 years later, to his general theory. But that's not subject of our today's talk. Our dialogue is about as you wanted it, and by the way, I didn't know that we're supposed to discuss Bohr's model of atom, so we're exploring it on the fly, in the flight, if you will.
I think it's a good way to explore.
Maybe. There is interesting historical fact. Einstein was obviously at the beginning of quantum theory, because nature of light is quantum. It's a wave, but it's a particle. Duality of light is such that photon is a particle of light, but it is a wave, meaning that photon, being a particle, is something small and local point, but wave is not. Wave is distributed across the space, and that was a real difficulty for Einstein and others, and French physicist Brillouin came with a solution. He came out with a theory that light is a dual, particle and wave. Well, I don't know who could be convinced with such simple idea, but
strange enough that today...
De Broglie. Sorry,
what I was going to say, strange enough, but today you may know nothing about physics, but you definitely heard at least once in your life. If you have nothing to do with science, you never took physics in the school, whatever, but you heard that light is both wave and particle. It's such an obvious, in quotes, fact. You think no? Because
it is not obvious,
no?
but it is indeed.
No. I mean, it's not obvious per se. But what I'm saying that everybody heard about that. It became very.
It's common knowledge.
Popular. Yes, it's like 2 multiplied by 2 is 4. Light is particle and wave. But let's go back to remember how people came to this idea and how complicated and sophisticated mind and mental process was in order to grasp it.
Indeed. So that discovery was by nature mathematical, but of course great physicists like Rutherford, Curie, others spend a lot of time measuring, creating, analyzing behavior of elementary particles, and they discovered beginning of 20th century, late 19th, beginning of 20th was very rich with discovery of new particles, alpha particle, electron, proton, and that was basically a result of evolving science of electromagnetic field and experimental power of high energy, high frequency.
By the way, the price was high because the story of Pierre and Marie, of Maria Curie, is one of the examples how people sacrifice their life for discovering the phenomenal things in nature.
So, beginning of 20th century, notably closer to 1920, 1910th, 1920s, the quantum theory started evolving. And that was difficult, because quantum theory was even more difficult to understand to ordinary mind than Einstein relativity. Difference being that Einstein relativity seemed to be not very important in terms of practice. Very few people had an option of moving with the speed of light or observing relativity phenomena. They were mostly cosmological nature, or astronomical, if you will, while quantum phenomena were quite observable. And that was painful because nobody understood what it is. Interestingly enough, Einstein didn't, and violently. He didn't want to accept quantum theory, although he was one of very few who actually created it, opened the gate. He even received his Nobel Prize in 1921 for his discoveries in the quantum theory of Einstein, Bose-Einstein condensation and otherwise. So that was initial theory of quantum liquids.
Not for theory of relativity, but for at least...
It's entirely different. He was not qualified, eligible to receive Nobel for relativity because Nobel was only given to discoveries proven experimentally. And general relativity was proved in 1921. The year he received Nobel for different things. It is interesting. That was his personal drama, or even tragedy, if you will, that to his end, Einstein did not understand quantum theory, and since he was semi-god of science, he didn't feel that he has to. Yeah, well, he argued. He argued with Bohr. Bohr was proponent of quantum theory, And quantum theory still to this day has primarily statistical interpretation. That all quantum matter, particles and otherwise, statistical entities. So waves that we're talking about, quantum nature of particles, not simply light, but other particles, is basically probability of them, those particles, being in certain place in space. It's not that particle.
And I remember the name, Planck. Yes?
Planck is a predecessor of quantum.
But was it him who actually formulated this? It's not even. It's like axiom. No, how can you call it?
Principle.
Yeah, principle of it, right?
Yeah.
Yeah, but it was related to electron only, in particular, right?
Initially to electron, yeah. And Planck came up with an elementary piece of space. It was not simply space. Electron has could be located only within a volume of space and momentum. So there is elementary six-dimensional, if you will, brick of space and speed and momentum that holds electron. More definitively, you cannot locate it, either speed or location. But if you locate electron, you cannot measure its speed. That was initial thought. Heisenberg, of course, participated in that, evolved that theory of Planck. But Einstein was arguing with Bohr, saying God doesn't play dice. Physics should not be interpreted statistically. It is clear science. Everything needs to be defined. Still to this day, general relativity of Einstein, his theory of gravitation, is not married with quantum. There's no link. Only now we're starting with discovery of Higgs boson, starting connecting gravitation with quantum. But it required a really huge collider in Geneva to come to that conclusion. $20 billion project. So it was obviously not attainable to scientists 100 years ago. But back to the theme of our conversation. There are plenty of very interesting and exciting things in physics, and atom is very important part of it, but nothing special, if you will. The only importance of atom is that it defines and describes matter as we know it. Materials, gases, liquids. And that's what we can observe physically. That's why it's so important. And experiments that greats of early 20th century done allowed Bohr to create almost philosophical model of atom in the form of atomic nuclei, surrounded by electrons. So and the Bohr was not great in terms of mathematics. He also was kind of philosopher. And that was the problem in his standing with Einstein. Neither of them could prove or disprove quantum. Einstein could not disprove quantum. Bohr could not because he was not a mathematician. But he saw clearly And he had quite a few very good theorists around him who developed and evolved this theory. So Bohr model was simple. It was nuclei which could be a combination of a number of elementary particles, usually protons, and protons is a heavy particle, about 2,000 times heavier than electron. One proton usually has elementary charge, electric charge, equal to in size but opposite sign to electron. An electron is another smaller particle which kind of surrounds proton. If we take atom of hydrogen, it's a proton surrounded by one electron. So electron and proton together create electric neutrality. But you can imagine it in the form of sun or particle surrounded by a cloud. At the same time, that cloud, according to quantum theory, is not a matter, but probability. And electron being particle, kind of probably somewhere around with certain probability, which requires different mathematics.
But interestingly enough, that matter itself is not a probability. Matter is the matter. It's a real thing. So it's interesting how the scientific view and interpretation of the nature and laws of nature smoothly transition to the real world, because obviously there is no any other way to explain the quantum world. If you don't, as far as I understand, you have to come up with probability, because there is no any other way to describe the matter on that low level. But when it comes to the macro world, to the world which we can observe and which is tangible, where does this probability go to? Where is there any boundary? How this probability shifts to the material world?
Sure.
Is it a stupid question?
There are smooth theories of connecting macroscopic and microscopic world.
Yeah.
And it could be distinguished by quantum parameter. When you move from atom, from electron and elementary particles, to solid matter or liquid matter in macroscopic size, to cubic inches or cubic or kilograms or grams or pounds, we perceive pound of matter differently than one atom. And the statistical nature of quantum dissolves when we think macroscopically. Why? Because big piece of matter contains so much of that probability, it becomes solid. But it's not a solution for a theorist. We can go deeper into that, and we will. But what's important, interestingly, of course, hydrogen is very simple. If you put two protons and distribute two electrons around, that would be helium. And interestingly enough, combining there are other particles necessary to provide stability and properties of atomic nuclei, neutrons, mesons, others. So theory of atomic nuclei also evolved significantly as we know it, but today we're talking about Bohr atom. And that brings us, interestingly enough, to a table of chemical elements, which Russian Mendeleev, he didn't discover it, but he kind of combined it, creating that table which explained positions and properties of chemical elements. And there are plenty of them. At the moment, about 130 known elements. Most of them stable, but some are extremely unstable. So 90 some, 99 or 100, about 100 are stable. The rest of them unstable because atomic nuclei is not stable. And main reason for difference in those elements is size of atomic nuclei, how many protons, neutrons, mesons, and others sit in that, and how many electrons distributed around. That brings us back to alchemists. If they knew that in order to create gold out of copper, they need to change atomic nuclei, and how much energy it takes, they might have been a lot more cautious about doing the experiments, because that is not chemical process. That is highly physical, doing that. So Bohr created that theory, model. It was not theory, it was model, with nuclei and distributed electrons, but it was not theory. Theory was created by great students of his, notably Schrödinger, Heisenberg, others who created mathematical equations to describe behavior of atomic particles, electrons, protons, others, especially, well, those Schrödinger equation, of course, describes all kinds of quantum matter, and they are nothing like classical physics equations. It's very interesting differential equation. But if you formulate Bohr problem, Bohr model, and envision atomic nuclei sitting in the center of the quasi-solar system, like Sun, and electron distributed around it, Schrödinger equation for electron could be formulated and solved. And solution describes magically entire structure of table of element system, why they have that distribution in the table, why they have such properties, because what we call quantum numbers of electrons in electromagnetic field of the nuclei really defined the orbits, the momentums, how many of them could exist in certain levels of orbits. They're those called orbital numbers. And that was the greatest success. That's why Bohr became such an important scientist and really figure in physics equal to Einstein, that properties of matter could be calculated like never before. You could solve Schrödinger equation and know how many electrons and what orbits, why let's say, in first layer of orbit could be only 2, and then, which is first level of table of elements. And y next could be only 8, second layer, and how it goes down with more and more orbits, because nuclei becomes more and more heavy and more charged.
Is it binary? Is it binary? 2, 8, 2, 8?
Well, no, it's not 2, 8, and then 32.
No?
It's growing. If a nuclei was stable below a certain level, it would be a lot, but it's starting falling apart, and that's how it ended. That's why we only have about 100 stable elements in nature, which is fun.
May I ask you a question?
What is important about it? Chemistry. Entire chemistry comes out. Sorry, I interrupted.
When we talk about nature, can we assume that number of elements which we have here on this planet is pretty much, or I will reverse my question. Is this table of elements propagates across the universe the way we know the universe? Can we assume that there is no anything which violates these rules and which is outlier, and everything everywhere in the universe, again as we know it, actually follow these rules? The matter is built the same exactly way. Any unknown or unimaginable elements which doesn't fall into these strict rules may exist in the universe. Possible?
Boris. That goes to nuclear physics, because existence of other elements entirely depends on stability of atomic nuclei. And that is due to properties of elementary particles like protons, neutrons, mesons, and others, which create and stabilize nuclei. Behavior of elementary particles in nuclei is not electromagnetic by nature. It's different. A field. It's strong field, but it has very little or nothing to do with electromagnetism. So anywhere in the universe, and behavior of those elementary particles does not depend on any conditions related to location or outside field. So when you, I will take it back. If you imagine place in the universe which can artificially, because of some field effects, can stabilize nuclei consisting of very many protons, neutrons, mesons, and otherwise, but only because of external conditions. Yeah, in that, like diamond, you can create artificial diamond. It requires a lot of pressure and very high temperature. You can create, and that's what science was doing for a good number of years, create super heavy elements, transuranic, we call them. At the moment, something like 130, I said. Those exist very fractions of seconds because conditions they require to contain elementary particles and nuclei as such. If you kind of universe place where those conditions are prevailing or can exist for longer than microseconds, well, super heavy elements could exist. But theory describes it anywhere. There's no other world, at least for now. Other world comes with a different theory, which goes really beyond particles. We're not touching it today. What's interesting and why Bohr is such an important, his model? Because it explains Mendeleev table, of course, the entire system of elements. But again, who cares? Well, just for knowledge. For practical purposes, what's important is physical and chemical properties of those elements in macroscopic form, not at atomic level, but how they create real matter we can touch and perceive. That comes with bonding. Atoms bond with each other. And bonding material is electrons. So electrons glue atoms to each other and expand throughout the structure to create matter in our macroscopic understanding, whether it's solid, liquid, gaseous, or even plasma. And when we perceive matter as a condensed state or something which we can feel and touch, it's because of electrons. And how electrons behave when two atoms or more comes together. What kind of bonding forms? It very much relies on Bohr atom and very much relies on Schrödinger equations. A remarkable success in calculating properties of matter out of first principles, which is amazing. You can really calculate why hydrogen is different than oxygen in terms of physical and chemical properties, how chemical compounds form, what is the entire chemistry, why it happens that way, because of bonding. There are several different kinds of bonds when certain atoms of different configuration come together and form chemical bonds. So it all evolves in a rather complex theory which can explain theoretically on piece of paper very significant observable behavior of macroscopic materials and processes like methods of molecular dynamics can explain phenomena of evaporation, solidification, detonation, flame and explosion could be understood and calculated, and new materials could be created on piece of paper and were created. And that's what made Bohr such an important person in 20th century. Still today we making exotic materials. Our airplanes built out of very complex materials, engineered, but in order to engineer those, you need to bring quantum equations and understand bonding. We create artificial diamonds and other artificial structures. They're not artificial elements. Artificial diamond is just a carbon, but it's then that's where structure comes, crystallography comes, because carbon could be graphite, could be graphene, could be diamond, could be diamond. And properties of graphene, which is quasi-two-dimensional material, are extremely important. It's very light and it's unbreakable. It's the strong material on Earth. And if we could create diamond in the manner of graphene, it would be even more so. And that's an example. So we fly with the composite materials based on carbon. We build cars, buildings, all our environment with the new materials, and those could only be engineered on the basis of that Bohr model. But back to the quantum. What's interesting, if in physics and chemistry you can use good and clear mathematics to basically calculate properties and effects and all that science produces, when you come to biology, it becomes a lot more intricate. Of course, biological molecules are a lot bigger than chemical, and we cannot calculate them completely just because of their complexity. Interestingly enough. Still, mathematics has major impact on biology in the form of biological statistics. So best mathematics can do for biology was achieved through biological statistics, or statistical biology, if you will. And that's a huge development with medical implications and all other things, classification and segmentation, which mathematics produces brilliantly. And now with the methods of artificial intelligence and neural nets, we're achieving a lot more, not understanding, but knowledge of biological effect. What entertains my mind, if you think of it, biology is so complicated it had to be perceived statistically, not deterministically. Maybe quantum is the same. Maybe we have to deal with the quantum nature of basic elementary matter just because it is too complex. So complexity that we still don't see.
It's interesting how the most complicated things which we may say life or living objects are. Probably life is the most complicated thing which exists in the material world. How it correlates in terms of scientific methodology for research with the quantum world. So the macro world in its probably extreme reincarnation, like a living creature, like an animal, like
Boris, you're absolutely right.
And then we go down to the very small things and we see the same.
That is a paradox. Biological effects are macroscopic. They're not microscopic. And still, complexity of biology, I don't know whether it's life. What we do know that biological molecules are very large. Even if there is no life, they are huge. And that's what makes it impossible to mathematize them throughout. They're too complex. Too many equations, and you cannot solve them all. not even on any supercomputer. But in the end, behavior of biological matter comes to some statistical observations. You can build statistical analysis and statistical equations, but biology is macroscopical. Quantum is not. The deeper you go into size and matter in space, more quantum it becomes. There was an interesting and productive scientist, American professor Wheeler, which tried to connect, to marry Einstein relativity with quantum. So what he basically was saying, philosophically speaking, that time and space are very complex, complicated structures. Space is not empty, and time is not. It's not just measures thrown across empty space and time. Quite opposite, time and space are form. It's very complex form. Like biological matter is something consistent of very complex molecules, time and space is a form consisting of very tiny topological units connected to very complicated.
One day I hope we will talk about time, and we're going to dedicate one of our dialogues to time in deep if possible, because it's to me it's probably the most mysterious things of anything you can think of. Yes, no?
Boris, yes, you're right, but space is as complicated as time. They basically equal.
Yes, because for me space is something which I can measure with steps, but it's not true, of course. It's a different thing. It's a different domain for this.
So work. I think importance of our dialogue today is a practicality of Bohr atomic model, atom itself, because other things we can practically live without them. We might not understand the nature of universe, and we possibly can live without it.
Yeah, because we are part of it, that's it.
But
even without
in our real world, we cannot live without airplanes, cars, and other materials and matter that we sense and perceive every day of our life. That's when science becomes imperative.
And just from what I know, what I read about Bohr and basically that times, I think it was very, I don't know if you can say this way, romantic time in science, because Bohr wasn't only was the scientist only. He created a school. There was tons of young scientists around him, like you just mentioned, a few just big names, but it was a real school, and people were just fascinated and mesmerized with his personality besides everything else.
Bohr.
Yes?
Bohr was a very interesting guy. First of all, he had 5 sons. So he was a community man. Secondly, Bohr was Olympic champion in soccer. I believe it was 1904 when his team won, Danish team won gold medal. Bohr was actually not in major, he was in reserve of that team, but his brother, Augie Bohr, who was almost as prominent as Niels, but he was a mathematician. He was even captain of that Danish team that won Olympic gold in 1904. And of course, Bohr, he was very warm, very kind personality. And because he was so well known, people came to his institute. Danish government raised funds and created Bohr Institute of Theoretical Physics in Copenhagen. And young scientists from around the world came to. Likewise, Leo Landau came to Copenhagen in 1931, I think, and spent a year and a half there. It changed his life. It made him great. It made him genius because he spent his time there, and he knew these people.
And he taught students in Kharkov State University very successfully. And we still have legends of how Landau was actually treating students in his university when he was a professor in Kharkov. It was a real trial to pass Landau's test.
Yeah, he was an asshole.
Yeah, that's true. That's true. Because I heard that stories from people who were his students in the university in Kharkov. Yeah.
Well,
Yeah. Yes, that was terrible.
Do you know how he ended up in Kharkov?
No.
When he returned from Copenhagen, he obviously was put to work at the Joffe Institute, Physics Technical Institute in St. Petersburg. And he worked hard there. But very quickly he came to a conclusion that Abraham Joffe, a very famous Soviet physicist, is not very bright. And he said so to his face, which basically led to his exile to Kharkov.
Yes, and he started teaching in the university, by the way.
Yes.
Yeah, he was teaching. He was, yeah, I think, yeah.
And eventually they created Physics Technical Institute in Kharkov, which was also very popular. But that's all in time. A different story.
Yes, it is. But somehow bounced from the Niels Bohr story, so you see, world is round. So as atom itself.
Several, I don't know whether it's related to our conversation, but several very bright Russian Soviet, young scientists in the very end of 20s, beginning of 30s, got opportunity to travel. Some of them, like Gamov, never returned. Some of them, like Bronstein, never. He was selected to go to Copenhagen, but never did because he was a nephew of Leo Trotsky. And Copenhagen Institute was a light for young, talented people who came together, and probably that was the most important thing. Together they created that beautiful science of quantum and nuclear and all other things that transpired back then. They probably would never do it without that unique opportunity. Likewise, later, and we'll speak about it hopefully in other dialogue, Manhattan Project, in a way, created greatness of American science. And those were not American scientists who created that greatness.
Yeah, that's true. Does this Bohr Institute exist nowadays, or do you know that?
Sorry?
Does Bohr Institute exist today?
Yes, it does.
It does, right?
It does. It's nothing. It is nothing like that.
Probably without Bohr.
Not because of that. Bohr was a very nice guy. Time time is a tricky thing. In history of science, the time in 20th century, middle of it, around atomic bomb, around thermonuclear and all those, generated a lot of talented people. There is no reason for us to think that there are fewer or lesser number of talented people now, but we don't see it. Of course, discoveries being made, inventions, all that beautiful stuff, but nothing like relativity. And if you look at history, Renaissance is another example. In a very short period of time, greatness evolved. Because why? Those greats of Renaissance, Raphael, Leonardo, Michelangelo, they lived in the same time. They knew each other.
Can we use Fibonacci numbers to see the wave of...
Fibonacci is not guilty. No, it's very simple. Atomic Manhattan Project created. It required humongous investment from American government to gather those people, most of them Germans, some others, very few Americans, who started working together and making discoveries. And so that was like a gold mine, which was exhausted. And although they tried everywhere, in the Soviet Union as well. First Soviet atomic bomb created gigantic splash and opportunity for Soviet scientists, which we enjoyed for some time. But global failure to create thermonuclear reactor because of natural reasons. It's not. It requires different science, different technology, another scale of energy. But we couldn't do it, and all that fashionability of science died out. And becoming businessmen and lawyers and doctors eventually became more fashionable.
I was a child in the 60s, but I remember very well what was how popular science and scientists were back in that time. And I think not only in Soviet Union, but across the world. It was really huge interest to this matter, and few things which we lost, I believe. The world lost interest to science and interest to chess. I don't know if chess is now that popular and as it used to be, but I think that in 60s, maybe it was a political reason too, but chess as a sport, which is the most intellectual sport, was under the radar. No more. As you said, time splashes and certain things are gone. But still, I think that still we may expect some huge things to be discovered, because what happened in 1920s and later basically changed the world. What next after Bohr theory of an atom can be of that scale?
Bohr.
Imagine.
We cannot live in Renaissance permanently.
Yeah.
Likewise in science, we cannot live in scientific Renaissance all the time. It would accelerate civilization incredibly. But we do. We had that splash. New science was created, fundamental became applied, went into technologies. Now we're enjoying a lot of inventions and expanding technology. We think that internet is as great as relativity. It is not. It's an entirely different thing. It requires different level of abstraction, but it's very useful. It created really environment which opens unique opportunities. So we're inventing now more than discovering. But back to education. Essence of our conversation is new generation. Every new generation needs to create, invent, discover. And all of us have our time. Today is a time of technology, inventions, and few who can will do their discoveries. And if those discoveries require energies which are not attainable to us today, well, they'll have to wait until we reach there. And if those discoveries opens for us understanding how our world exists, how space and time form, and maybe even open portals to other space and times and universes. Not only it requires different energy, it requires different mind. Can you imagine today's man traveling in time or space and universes? Does make sense. So we have to grow.
And not only today's man. I have a strong sense that for a long time ahead, it didn't happen because I don't feel like anybody came from the future to say hello to me yet. So, which means that probably in the observable time period, it didn't happen yet. And maybe it will never happen, but that's different.
It did not happen, not necessarily because it's not impossible, because it's not possible. It might not happen because it does make sense. What man of the future has to do here? Why?
Oh, I know a few reasons. Scotch, for example, tequila.
We see it all in movies, Back to the Future. Evidently, we have nothing to do with it.
By the way, it's a joke, of course, but you know what? But not that much of the joke. I just caught myself on my personal attraction to the movies which are related to traveling in time. Even though it's almost always the same scenario, and you kind of can foresee what's gonna happen. You feel what is the narrative, but it's still so fascinating to me, and it's still so mesmerizing. It's still so attracting. So every time when there is a movie, especially a good movie with these time traveling things, it really had a lot of magnetism. It just attracts me personally, because probably it's my personal area of interest, because, as I said, time is something which really makes me sad.
Have you ever read, probably did, Yankee at the Court of Arthur?
That was the first thing which amazed me, because this paradox of people from different era came in across technology collision, knowledge domain, and oh yeah, of course. That was very interesting experiment.
You see, simplicity, simple-mindedness of a man, either back into Arthur times or even today, is a different scale than complexity and sophistication of science required to travel that way. Basically meaning that a person, if we can imagine that, from the future, or maybe from the past, who knows how to travel in time and space and universes, has nothing to say to us. That makes sense. We'd like to speak to them.
Yes, but they don't like to talk to us.
They know us throughout. Likewise, we don't want to speak to mouse. They, yeah. You have too much appreciation of yourself, like all of us. We think that we're worth such a conversation. They don't. That's almost like thinking of God. We think it would be very nice if we could have conversation with God. God doesn't think so. Okay, I think we have fun.
Absolutely. Thank you so much. As always, it was very interesting, and I learned a lot. As that movie which we mentioned, which is back to the future, to be continued.
Let's cut it. Мне бы хотелось как-то приблизить к нашей educational agenda. Я, откровенно говоря,